Hello, good afternoon. Are you all able to hear me? So we are all set for today's class. And as you can see, what I have already written over here, today we are going to know about or learn about Schrodinger's equation. And Schrodinger's equation basically has two forms. One is called the time-dependent Schrodinger equation, which I have written as the TDSE. We will be talking about this today, time-dependent Schrodinger equation, as well as we will see that there is another form which does not have explicit presence of time in it, which is called the time-independent Schrodinger equation, written as TISE. All right. So today's class has begun, and I hope you all will be able to learn what I intend to teach you today. Okay. So we are once again telling you all that we are going to talk about Schrodinger's equation. Now, reminding all of you about the last day's class, what we had seen that for every measurable quantity in classical mechanics, there is a particular operator in quantum mechanics, right? And we had seen how an energy operator looks like. We had also seen how momentum and position operators look like. Now, all said and done, we have talked about the wave function. We have talked about operators. But the question arises that how do we know about a particular wave function for a system? Are you trying to get my point? The question that I am asking here is that suppose I want to know what is the wave function of an electron in a hydrogen atom, or I want to know what is the wave function of an electron in some other system. Until and unless I do not have the information of the wave function, neither will I have any information about its probability. Remember, mod chi square. I will not have any information of that particular object. Similarly, I will not be able to ask any operator to act on the wave function and give us the values. So before we act any operator on the wave function and find out its value, our first agenda will always remain about knowing the wave function for a particular system, isn't it? And this is where actually we come to the Schrodinger's equation. So what is basically Schrodinger equation? Schrodinger equation is an equation solving which we get the wave function for a particular system. I will give you an example. Forget about the quantum mechanics right now. Suppose I am talking in classical world. I want to know how a simple harmonic oscillator is working. What will I do? If I want to know what is the position of a simple harmonic oscillator, what do? We generally write the equation of motion. Remember, we write down the equation of motion. Let me just write it. It will be easy for you to understand. Say, I generally, what do I write? I write m d2x dt square. This is mass into acceleration of the particular system or the harmonic oscillator that we were talking about. And this we equate to minus k into x. Remember? So this is the inertial force equated to the restoring force. And this eventually brings us to the equation of motion. So m d2x dt square plus kx is equal to 0. This is the equation of motion of a simple harmonic oscillator. And when I want to know the position, what will I do? I will solve this equation and I will find out what is the x, right? But now my question is, how will I know about the wave function? Which means this, taking a clue from this equation, can we now not write or have an equation where we will be solving, where psi will be there, where the wave function will be there in that equation. And when we solve that equation, we can find out the wave function, we can find out that psi. And exactly this is our Schrodinger equation. So Schrodinger equation is actually the equation of, you can say motion, equation of motion of the wave function, which is followed by the particular wave that we are talking about. So when we talk about Schrodinger's equation in quantum mechanics, we are actually talking about the particular equation which is followed by the wave function. And when we solve this Schrodinger's equation, it gives us as its result, it gives us the wave function of our particular system. So is this clear now? So what is Schrodinger's equation? Schrodinger equation is the particular equation solving which we are going to get the wave function of any particular system. Fine. So, so I can see many messages over here. So which means we are all listening. Fine. So now let us get back to our studies. So again going back to the Schrodinger equation. So where do we start from? Remember when we were discussing about Schrodinger equation or quantum mechanics initially in our group, Triti Nabo had said that what is this Schrodinger equation, ma'am? And I had said that actually Schrodinger equation is another form of writing down the total energy. So let us now understand why I had said that particular line at that time. So let us begin with a classical equation. Classical equation as in an equation which you all know, which we all will agree can be written either in classical mechanics or in any particular mechanics. What is that? I can write down what is the total energy. I hope all of you will agree with me that kinetic energy plus potential energy is the total energy of any system. Do you all agree with me? So this equation when I write basically has been written in the classical terms because we have written down the names of the measurable quantities. What are the three measurable quantities I have mentioned here? I have mentioned about the kinetic energy, the potential energy as well as the total energy. Fine. Now when I want to write the same equation in quantum mechanics, what will I do? Can I write a measurable like this? Remember, no. In quantum mechanics, when we write about measurables, we don't write them as their names, we rather write them as their operator forms. Right? So, how will I write? I will be writing it as the kinetic energy operator. Remember, putting it as a hat, kinetic energy operator plus potential energy operator is equal to the total energy operator. So, as if I have brought the classical equation to the quantum world. But reminding all of you once again that any operator does not have any physical meaning on its own. It will only give us any meaning, it will only give us any value when it acts on the wave function. Correct? So, this equation actually has no physical significance. This will become significant when this energy will be acting on a wave function. This energy operator will also act on a wave function. Right? So, kinetic energy plus potential energy is equal to total energy. That equation in classical mechanics gets a new form in quantum mechanics in this way. That is the kinetic energy operator plus potential energy operator acting on our wave function is equal to total energy operator acting on the wave function. So, is this up to here everybody has understood? I just want some responses, otherwise it becomes a little difficult for me to go forward. I want you all to understand and only then I want to go forward. Yeah, Arjun has some doubt. Arjun, can you please say what is your doubt? Is Arjun about to write his doubt or shall I go forward? Okay. I'm getting a lot of yes ma'ams. So let's go forward. Arjun, we can talk about it later when we are discussing. Fine. So this is where our equation in quantum mechanics is now standing. But then when I write kinetic energy operator, kinetic energy hat, potential energy hat, this is just another name again. So now it is time for us to know how does the kinetic energy operator looks like or how does the potential energy operator looks like. Only then when we put these forms into the equation will be complete, isn't it? However, just reminding all of you, we have already seen how the total energy operator looks like. I H ka del del T. Remember we had done in the last class? So we will be using that information today again. But before we put that information there, let us first understand how will the kinetic energy operator look like in quantum mechanics. Fine? Arjun is asking, ma'am, is Schrodinger equation applicable for big particles like us? Now, this is a very good question. Once again, this answer is same as, do we have waves? Do big particles like us have waves? See, Schrodinger equation is the equation which is followed by the wave. right? It is followed by the wave function. So when I have a prominent wave or a prominent wave function which I cannot neglect, I will be using Schrodinger equation to solve it. But for systems like us, where our waves can be neglected, Schrodinger equation does not have any very significant role to play with. Our equations, or when I want to know my position, I can do it in the classical manner only, isn't it? So for large systems, this entire quantum mechanical theory does not hold very significant. Quantum mechanics is basically significant for microparticles, isn't it? So I hope you have understood, Arjun. So let us go back to answering the question that how does the kinetic energy operator looks like. Fine. Now, reminding all of you, we have already seen that the momentum operator, if I am writing in terms of the x-axis, that is the kinetic energy operator, along the x-axis is px, and how did we write it the last time? Minus ih cut del x. Remember, we had already derived how we got this. Keeping this in our mind, now I want to go forward to derive the kinetic energy. Now, in classical mechanics, what is kinetic energy? I know all of you will answer me that kinetic energy is equal to half mv square, isn't it? Half mv square, or I can say p square by twice m. So, kinetic energy is half mv square, or I can also write it as p square by twice m, since p is equal to mv. Correct? Now, if this is my kinetic energy, remember, since we are doing this in terms of our one-dimensional motion, we are doing this for one-dimensional motion today. I did not mention it earlier. So please understand the fact that whatever I am talking right now is in terms of a one-dimensional motion. Our wave function is only a function of x and t. And this half mv square or p square is also then not the total momentum, not the total velocity, rather it is the x component only. I hope you are all good with this. So in this scenario, at this point, I am asking you, what is the operator form of kinetic energy? See, kinetic energy is p square by twice m. But I know what is the operator form of momentum. I know what is px. Then can I not find out what is p square by twice m in the operator form? Let's do that. Let's see how it looks like. So this is the particular value p square by twice m that I want to translate into the operator form, right? And remember, just a few moments ago, I had written that what is this px? When I write in terms of operator, this px looks like minus ih cut del x. So what will be p square? What will be px square? A square of this entire thing. And then what will be p square by twice m? It will be twice m of this. So minus ih cut del x whole square divided by twice m will be the operator form of kinetic energy. I hope all of you are understanding. So can I not write kinetic energy operator as minus h cut square by twice m del 2 del x square? See, is this making sense? Because I have taken a square of minus I, minus and minus have become positive, but I into I has given me a minus 1. So that minus 1 is coming over here. H cut has become h cut square. This twice m we have divided, we have got it from here, p square by twice m. So this twice m is in this case, and del 2 del x square is coming from the square of del x. So the kinetic energy operator in quantum mechanics is minus h cut square by twice m del 2 del x square. Is this clear to everybody? Are you all understanding? I can see a few unknown names, not from our class. Hello, Shotrik. I hope it is helpful for you as well. So this is where we are standing at this moment, where we have derived or where we have seen that how we can find out the kinetic energy operator when we know the momentum operator, right? So this brings us, let us get back to our Schrodinger equation then. So when I take this value and I put it into this equation, I'm getting closer to the real form of Schrodinger's equation. So writing Ke cap is not going to suffice when I want to write the Schrodinger equation. I will have to write this part. So now what will we do? We will write it as minus h cut square by twice m del 2 del x square acting on my psi. So kinetic energy operator acting on psi plus potential energy operator acting on psi is giving me the total energy into psi. However, now the question arises, what is the potential energy operator? Isn't it? Are we not now thinking that after we have written down the operator form of kinetic energy, it is now for us to write down the potential energy operator? But here lies the problem. If you call it problem, it is a problem, or you may say a complication. And what is that? Just think about the situation that when I asked you what is kinetic energy, all of us had only one answer, half mv square. Potential energy of any system, whether it is moving under a force, electrical force, magnetic force, when I'm pushing something, the kinetic energy is always having the same formula, half mv square or p square by twice m. But stop and think here. What is the potential energy? Do we have a single formula for potential energy? Is it possible? The answer is no. Potential energy is different for different systems. Suppose this is my reference point. I am taking this pen from here till a height of say z. What will be the potential energy of this pen? mg into this height, mgz. Suppose these two are two charges. What will be the potential energy of these two charges? Q1, Q2 by R, where R is the distance between them. See, so as many systems we count here, the potential energy gets different from one another, isn't it? So when I have to actually write down the potential energy operator, I cannot have a universal formula like half mv square p square by twice. For potential energy, every system has a different potential energy, and so we cannot write any particular or unique form of potential energy operator as well. So in this equation, whenever you are writing down the Schrodinger's equation, this part remains constant because kinetic energy is this form for every system. Total energy is also like this for every system. However, potential energy part is different from one another as we move from one system to the other. Right? So let us get back to writing down. So how do we write potential energy here? We will be, in general, all of us know that potential energy is written as V. Remember in classical mechanics also, we used to write, every time we used to write about potential, we used to use this very notation of capital V, right? So we are going back to this. So we will be writing the potential energy operator as a V cap. As a V cap, right? And it obviously has to work on the wave function. But one more thing I would like to add over here about the potential energy, which is very, very interesting and which is also very, very important. You should never forget that. And what is that? See, when I asked you what will be the potential energy for a system, say when I'm moving it by a distance, it was mgx. When I said about electrical system, it was Q1, Q2 by R. So all these potential energy formula or the potential energy values are depending on which quantity? Remember, they are depending on the position, isn't it? Either directly proportional to x or inversely proportional to x. But in some form or the other, the potential energy for any conservative system is only dependent on the position, isn't it? So, in our Schrodinger equation, when we are writing, you will see that always we use this kind of a notation, that this operator, however it might be, whatever be its form, whatever be its formula, finally it is a function of the position only. Okay, since we are writing down or we are talking in terms of 1D, we are writing it as a function of x. If it was in terms of 3D, we would have written the r here. Fine. So this is how the Schrodinger equation looks like. And if I now put the value as we had derived the other day for E, what do I see? I see I h cut del t of psi xt. This is the energy operator acting on my wave function. So this is the right hand side. So see once again, we started, where did we start from? We started from writing down kinetic energy plus potential energy is equal to total energy in classical mechanics. But now we have completely taken that classical mechanical equation to a quantum level by writing the operator forms. And this very equation is our Schrodinger equation. And how does it read like? Please all of you note down, minus h cut square by twice m del 2 del x square acting on psi. The potential operator acting on psi is equal to total energy operator acting on psi. So this is the so-called Schrodinger equation. And as you all will agree with me that we are having explicitly the presence of time in this, this is called the time dependent Schrodinger's equation. Okay, so this form, from now onwards, wherever you come across this form of Schrodinger's equation, just remember this is which form? This is the time dependent Schrodinger's equation. So if the question comes that derive time dependent Schrodinger equation, this is the equation we are asking you to derive. I hope all of you have understood. Okay. Okay, very good. Now, if you remember, when I just began, I had told you that Schrodinger equation also has another form, which is called the time-independent Schrodinger equation. This is what we are now about to start. We will see how we can convert or how we can get the time-independent Schrodinger equation from this very fact, from this very equation. So, up to here, everybody has understood? Nawaz has asked a very, I would say, difficult question. How do we calculate the kinetic energy of a light wave? We will talk about it in our group, okay? Because it is again a very interesting topic. I will talk about it. Fine. So most of you have said that you have understood. So let us go forward. Now the question is, beginning again or going again to the question which I had asked you, that why do we require Schrodinger equation? We require Schrodinger equation so that we can solve this equation and we can find out what is this psi. What is this psi? Right? And what is this particular wave function that we are talking about? It is the wave function of the system that we are interested in, that we are working for. Remember, if you see over here, this wave function is a position dependent function as well as it is a time dependent function, which means this psi is a function of two variables, time as well as position. Now, solving these kind of equations where there is x, where there is position as well as time, obviously is complicated because we are solving for one variable, which is again a variable of, which is depending on two different variables, position and time. So how do we do? Why do we complicate our lives? What we are now going to do is to simplify this thing, which means we are going to go from an equation where there is time, where there is position as well, to an equation, or rather to two equations, one which will have only time and the other which will have only position. And obviously solving an equation with only one variable will be much easier for us. And that brings us to why we actually need the time independent Schrodinger equation. Actually, we are trying to separate the variables. Please remember this term, separation of variables. Since this equation as well as our wave function depends on two variables, position and time, now what we are going to do? We are going to separate out the variables. We are going to go to a scenario where we are only having a part which is dependent on position and another part which is dependent only on time. So let's begin. Okay. Because of the small space over here, so many times I have to rub this. Please bear with me. So let us again write down that this wave function is a position of, is a function of position and time. So what I am writing now is I am going to write this as a product of two functions. I'm going to write it as a product of two functions. Say psi prime, which is a function of position only, and say phi, which is a function of time only. I hope all of you will agree with me that we can do this. Now, since we are going to, I want to write for the wave function part, I want to write psi. I want to write this psi so that it becomes more important. Rather, what I am doing, I'm naming the position dependence as psi, and let us have the name of the total wave function as psi prime. Was this a bit confusing? Please see what I have done. I have taken down a wave function, a complete wave function which is a position which has dependence on position as well as time, and then I have written it as a product of two functions. One is a function dependent only on position and the other is dependent only on time. Can I not write this? Let me give you an example, a very easy example. Remember last day we were writing the wave function for a free particle. I had told you that how does it look like? It looks like e to the power minus I kx minus omega t. We had a amplitude as well. If this is my total wave function, this is a function of x, this is a function of time as well. But can I not write it like this? Into e to the power I omega t. So as if this part is only dependent on x and this part is only dependent on time. This is exactly what we have done in case of the general wave function as well. We have written down it as a product of two terms, one which is only dependent on position and the other which is only dependent on time. So is this clear? What we have done is we have separated the variables. We have written the total wave function as a product of two terms, where each of these individual terms depend only on either position or either time. Fine. So with this, let us move forward. Let us go back to our Schrodinger equation once again. So what I will do, I will write it as minus h cut square by twice m del 2 del x square. I'm not writing function of x and function of time once again. I'm just writing product of this because this is my total wave function. A function of x only, a function of time only. Plus the potential energy operator, which is a function of only x, will also act on my wave function. And my total energy operator will also act on psi and phi. So when I have written this, I hope all of you have understood. This is what I mean. Instead of the total wave function which was dependent on time as well as position, I have written down it as a combination of two terms or a product of two terms. This psi over here is only x dependent, this phi over here is only time dependent. Now let us get back to the mathematics. Now see, now this operator, the del 2 del x square will be acting on my psi, right? But on my psi, I have two parts. This psi, which is having some dependence on x, and this phi, which is only dependent on time. So will del 2 del x square act on phi? No, because phi is constant in terms of x. So I can keep this phi outside of the operation, just like a constant factor. So may I not write it like this? Writing phi minus h cut square by twice m del 2 psi del x square, right? Once again, now this potential energy operator will act on our products. Once again, this potential energy operator also has only what dependence? Only x dependence. So this V will also act only on the psi. It will also not be acting on the phi part, correct? So once again, can I not write it like keeping phi aside, V acting on psi? Correct? But when I come down to the right hand side, this operator del t, will del t act on my psi? Because psi is a function of x only. So del t has nothing to do with x. So I can keep this psi as a constant outside of my calculation, and this ih cut del t will only act on phi. So everybody is understanding the fact? Yes, Shrestha, I just changed the name because in all these I would have to write psi prime so many times. I wanted to reduce my word, so I named the total wave function as psi prime, and over here I have written psi. I have reduced my work a little bit. I hope you can understand. Fine. Okay, so this is where we are now standing. Now, at this junction, at this position, I want all of you to divide this equation by phi into psi. Divide this equation by psi into phi. So what will I get if I divide this by phi into psi? I hope you will agree that in this, I will be left with only 1 by psi. Similarly, over here also, I will be left with only 1 by psi, and when I come down to the right hand side, because I had a psi standing outside, when I divide it, I'm going to have a 1 by phi. So up to here, everybody has understood? Now look into the equation. This equation has become very, very interesting at this point. When I look into the left hand side, this left hand side is only depending on x. See, whether it is the potential energy, whether it is del 2 del x square, whether it is the function that we are working with, everything only is a function of x. Only there is the presence of the position in the left hand side. On the other hand, when you look into the right hand side, this is only time dependent. There is no position dependency here. There is no x here. So we are now looking at an equation where the left hand side is only position dependent and the right hand side is only time dependent. Two different variables. One part is only depending on t, the other part is only dependent on time. So as if we have already separated out the two variables as a left hand side and a right hand side. Isn't it? Isn't this interesting? And this is where we are now ready to go to the next step. And what is that? Please listen carefully. Any equation like this, where the left hand side is only a dependent of position and the right hand side is only a dependent, has the dependency of time, a separate variable, and that too they are now equal to each other. This can only happen when individually left hand side as well as the right hand side is equal to a constant factor. Okay? When this is the scenario, repeating once again, when I have the left hand side as a function of position only, being equated to a part in the right hand side, which is a function of time only, this is only possible when individually left hand side as well as right hand side is equal to constant factor. And think about the question now. What can be this constant factor? The answer is energy. Remember, what is this? Finally, we have started everything from energy, potential energy plus kinetic energy, total energy. So this equation, when we are equating this to a constant, it is nothing but the energy of the system, which I can write as E. This is the constant. Remember, energy is conserved. We all know from the very beginning, from class 5-6 days, that energy is a constant, energy is conserved. So the left hand side of this equation can be written as E. The right hand side of this equation can also be written as E, where E is the total energy of the system. And when I say total energy of the system, I mean the value of it, not the operator of it. This is the value. This is the constant value of the energy. Fine. Now, let me just concentrate on the left hand side. Please concentrate on the left hand side only. 1 by psi minus h cut square by twice m del 2 del psi x square plus this is equal to E. Can I not take this 1 by psi to the right hand side? Very easy. So let us take this psi and write it over here. So please see, all of you, what did I get? I have actually written down an equation. See, writing once again, minus h cut square by twice m del 2 del psi del x square plus v psi is equal to E psi. This equation is nothing but the time independent Schrodinger's equation. Why am I calling it time independent? Do I have any time over here? No, because the left hand side is only dependent on the variable x. The right hand side also has the wave function. This wave function is only the part which is dependent on x. So from the time dependent Schrodinger equation, we have come down to an equation which is completely independent of time, and this part is called the time independent Schrodinger's equation, or TISE. So is this clear? Very good. Very good. I hope my students are understanding. Fine. Now, I will not be leaving out the right hand side as well. This right hand side also is individually equal to E psi. I mean, sorry, there is no psi here. This right hand side was also equal to energy. And when I bring this phi over here, I can write another equation as this. So remember, where did we start from? We started from the time dependent Schrodinger equation, where the wave function was depending on position as well as time, and the equation also had del 2 del x square, del t both. But from there, by separating the variables, by the method of separation of variables, what we received? We have received two separate equations. Solving this part, I will get the position dependent wave function, and solving this, I will get the time part of the wave function. So finally, if I ask you what will be the solution of my system, I will solve for psi, I will solve this equation for phi, and finally my total wave function will be a product of these two, psi into phi. So when we are solving a particular system Schrodinger equation, we do the exact method like this. We separate out the variables, we solve the time part separately, we solve the position part separately, and finally to get the final result, we just take a multiplication of both the results. Fine. So is this very difficult? I hope this is not difficult at all. If you understand, this is very easy, and this is where we are now standing. This is the form which we call it as the time independent Schrodinger equation, and this is the time part of every Schrodinger equation. Now this brings to a very, very interesting fact. That is, just like kinetic energy, when I said kinetic energy, every system had p square by 2m. But potential energy varied from one system to the other. Now, if you look into the second equation over here, IH cut del t, this is the total energy operator, is equal to E phi. Isn't this equation same for everybody? This equation, in fact, has no difference for a system which is in an electric field to a system which is in a different field. This particular part, this time part of the wave function actually is same for every system that we can think of. Fine. So this equation can be solved once, and this result can be used for every system. Right? Thank you, Arjun, for saying not difficult. I'm glad to hear that. And going back to the lesson once again, that this time part of the wave function for any wave function is the same, and if we can solve it once, this result can be used forever for every system. But what is difficult, or what is different from one system to the other? Remember, this potential energy. This potential energy varies from one system to the other. So the potential energy operator also varies from one system to the other. And so the position dependent wave function part is actually different from one system to the other. So this is the part which is actually differentiating one system from the other. Fine. So in today's class, all we are going to do is to solve this time part. And from next class, we are going to look into how to solve the time independent Schrodinger equation for given systems. So this part is for the next class whenever we are having that. And as a last point in today's class, we are going to solve this equation, which means what am I solving? I am solving the time part, the temporal part of any wave function. Why am I saying any wave function? Because this particular solution is applicable for every system. Fine. So this is the equation which I now have. So see, how is it looking like? there is an operator which is acting on a function, pulling out a value and giving a function. Remember, can I not call this as the eigenvalue equation? An operator acting on phi, giving out some value and the phi is returning back. So this is again an eigenvalue equation. And we are now ready to solve this so that we know what is this wave function part phi. Now let us see. I hope all of you will agree with me if I write del phi by phi. I'm bringing this phi to the left hand side and I'm taking the rest over there. So E del T IH cut. Is this legible? Okay. So in the left hand side, I have del phi by phi, which is equal to total energy E by IH cut del T. Now I would like to ask you all to integrate this. So let us integrate this function. So what will I get if I integrate this? Del phi by phi will be simply ln phi. I hope my formula is right. You all know I'm so bad in maths. And when I integrate, this total energy is a constant. IH cut is a constant. So the only variable is delta T. And what are we left with then? E into T. But remember, this equation was what kind of integration? We did not have any limits. So we must be having a constant here. Fine. So what do we have now? Ln of rho is equal to this constant. Now, how will I remove this? So I hope all of you will agree with me if I now write that phi is some constant e to the power e by t IH cut, where what I have done, I have taken this constant in such a manner that I have added it like a amplitude. That is also a constant part. So while solving for the time part of the Schrodinger's equation, I have received the solution, which is this phi, which is a function of time only, is a constant c e to the power total energy E by into time divided by IH cut. In case I don't want to write this I in the denominator, I could do this. I into I will give me a minus. Sometimes you will see that this form is also written for the time part. Okay. So the time part of every wave function looks like so. Time part of every wave function belonging to any system is a constant e to the power minus I by h cut e into t. So from now onwards, whenever we have to solve for the Schrodinger equation, we will use this time part in every solution. Individually, we will find out the position part, and once the position part is known, we will multiply this time part and we will be good to go. So I hope everybody has understood whatever we learned today. Reminding all of you, from where did we begin? We began with Schrodinger's equation. We began by deriving it by total energy. Kinetic energy plus potential energy is equal to total energy. From the classical counterpart, we came to writing the operator forms in classical mechanics and we received our Schrodinger equation. Right? That Schrodinger equation, remember, was having explicitly the presence of time. So from there, we separated out the variables. We separated out functions which depended only on position and dependent on time. And using the method of separation of variables, we received the time independent Schrodinger equation. We also got the time part of the Schrodinger equation and we solved it till here. So that's all that I have to tell you today. Acha, why it was called time dependent? This part only has time. So this is time dependent. Okay. Pratyay is asking, is this derivation part need to be remembered? Sometimes questions do come. Derive time dependent Schrodinger equation, derive time independent Schrodinger equation. They do ask you. They do ask you. And see, if you just know the steps, if you've understood how I have done this, I hope it is not going to be very difficult. Please don't take it as like you have to remember and write. Please understand the steps. Okay. The more you practice, the more it will be easy for you. Fine. That previous equation which was without t. I cannot understand. This is Debargo, I guess, right? Mm, I suppose you are asking about this. See, what we had started from. We had a total wave function which was dependent on position as well as time. And then we had broken it up into two parts. One function which was only a part of x and the other function which was only a part of time. This psi, whatever the equation, this psi that I have used earlier, this was only dependent on x. It did not have time. For my simplicity, so that I did not have to write once again, I had named this psi as a function of x only. Okay, is this now clear? Okay, okay. I have misunderstood someone else as Devargo. This is someone else. I don't remember the ID. Anyway, is your question answered? The previous equation, which was without t, it was only having position, it was only having x dependence, so we were calling it as the time independent Schrodinger equation. Okay, okay, yes, yes, I should have remembered it is Shobik. He is the one who is our gamer, right? Shobik, so your answer is your question is answered. Very good, very nice. So that's all I would like to tell about. Pratyay, as you're asking, can it be done? Yes, yes, it can be done. If I have, say, a solution which is dependent on position and on two different variables, we can always use the method of separation, the separation of variable. We can use this. Very nice. So now that all my students have understood, I'm very happy. So let's call it a day. Bye bye. Take care.